Good day, grade 12s. Today we're going to be starting a new topic called equilibrium. But before we talk about equilibrium, I want to talk to you about what I'd like you to do at home for me. Just a bit of practice for rates of reaction. So if you recall, we are on exercise 5.1 and that's on page 109. And I'd like very much for you to do question 2. So please do question 2 of exercise 5.1 on page 109. It's a rates of reaction question and I'd like you to work through that for me. All right, let's look at today. So today I want to talk to you about equilibrium, and before we get started, there are a couple of key words that we need to pay attention to and that we need to be completely familiar with. So the first one is the concept of an open system. Now, an open system means that particles are allowed to escape. So if you had a beaker, okay, and that beaker was filled with water, you wouldn't have a cover on it. That would be an indication of an open system, okay, which is the example that we have here. I want to use a more realistic example for a moment. Imagine if you had a pot of water on the stove, and you had a heat source going and that water was boiling. If you have the cover off or the lid off of your pot, that would be considered as an open system. Okay, and what would happen is that the water would evaporate and then the level of the water would decrease. I'm sure you've seen this happen if you're ever making anything on the stove, that the water then decreases because of evaporation. Very few, if any, of the vapor molecules return to the actual liquid phase. So once they become gaseous, they leave the container and do not return. Now the next type of system that we're dealing with is one that's referred to as a closed system. Okay, when we talk about a closed system, it's a system where the particles are not allowed to escape. So we have a system where it's sealed, all right? So if we were talking about a beaker with water, it would have a lid on it, and that lid would prevent any evaporation or any water molecules that have evaporated from leaving the actual system. If you were going to use that example of a pot with boiling water, it would be very similar to that, except now you'd have a lid on the pot. If you've ever done that at home, you'll know that you often see the evaporated liquid condensing on the lid of the pot. So you often see that on the inside of your container. So the example of water in a beaker with a lid, the water molecules evaporate, but they do not leave the system. The water level remains constant after a while. So after a little bit of time, once the evaporation and condensation vibe has been set up, then the water level will remain constant. And the reason for that is that the water molecules condense at the same time as other molecules are evaporating. So you have this system where you've got stuff evaporating and stuff condensing, and that concept or that idea of evaporation happening and condensation happening is this whole idea of a closed system. All right. We can say that dynamic equilibrium has been reached. Now the term dynamic equilibrium means that the rate of the evaporation and the rate of the condensation occurs continuously. All right. So this dynamic equilibrium is reached when the rate of evaporation and the rate of condensation are the same. They're equal to one another. Okay. If we want to represent this by using some chemical formulae, we can see that if you've got the liquid to vapor and the liquid to gas, all right. It's very interesting because this is one of the first times that you've seen a double arrow in science. Now this double arrow here simply means that the reaction is reversible, that both things are happening at the same time, which means liquid is becoming vapor and vapor is becoming liquid. So that is what that double arrow means. We remember what the subscripts mean: L for liquid, G for gas. So this is the equation that represents this concept of dynamic equilibrium. Now this concept of using this double arrow brings us to something that we haven't actually discussed very often in science class, and it's the concept of a reversible reaction. So when I talk about a reversible reaction, what do I actually mean? I mean that the reaction is able to happen and then it's able to reverse itself. These are not chemical reactions that we are completely familiar with, because most of the time all of the reactions that we've done in the lab have gone to completion, which means if I burnt magnesium ribbon in oxygen, you would see the magnesium ribbon burn, and then you'd see the magnesium oxide formed, and then the reaction would be done. But what we're talking about here is a concept where, okay, and this one isn't exactly possible, but where the magnesium ribbon would burn and become magnesium oxide, and then the magnesium oxide would become ribbon again. Okay, so a reversible reaction, this is an example that I have here. It's hydrogen gas and iodine gas, which creates hydrogen iodide. Now, what you must remember for a reversible reaction is that it's not a case of all the reactants forming product and then all the products forming reactant. It's actually an ongoing thing where some reactants form products and then some of those products form reactants again. So the whole back and forth of the reversible reaction is happening continuously. So the hydrogen and the iodine react to form two molecules of hydrogen iodide gas. That's that first one. When the hydrogen comes into contact with the iodine, the forward reaction will take place quickly as the concentration of both are very high. Now, this idea that says the concentration of both are very high, initially, remember what we were putting into the reaction vessel is hydrogen and iodine. And that's why they've got those two things initially as very high concentration of reactants. As the reactants react, so the concentration of the reactants will decrease. Now, I want to show you this in light of a little picture, actually. Okay? So, let's look at this picture. So the hydrogen and iodine, okay, they react with one another to form hydrogen iodide. Oh, I'm so sorry. I just need to rewrite that. Okay. So the hydrogen and the iodine form hydrogen iodide. This is this first forward reaction. So this point over here is the beginning of the reaction. That means you've only got reactants in the reaction vessel, and as they are reacting, you can see there's less and less and less of them available. Okay. But the moment you start using reactant to form products, that's the point where the products start increasing. Can you see that? So it's almost like as the one thing decreases, the other one increases. And we get to a point here, which we call our equilibrium state, whereby the production of product and the production of reactant is equal. Okay. So the hydrogen and the iodine reacts to form hydrogen iodide. And when the hydrogen comes into contact with the iodine, the forward reaction takes place very, very quickly as the concentration is very high. As they react, so the concentration of the reactants will decrease. You can see it becomes less and less. The rate of the forward reaction decreases. Hydrogen iodide is an unstable compound which can easily dissociate to form hydrogen and iodine. So once we've got any of this hydrogen iodide formed, it dissociates to form the hydrogen and the iodine again. The reaction is therefore reversible and is represented by this. Okay, so the curve illustrates the reaction for both of the reactions. The forward reaction is initially fast but slows down as more products are formed, and the reverse reaction starts at zero because initially in the container or in the vessel you have no product yet. The reverse reaction starts at zero but speeds up until the two opposing reactions happen at the same rate. Okay, they happen at the same rate. Now, to give you an idea of this from a very, very real perspective, if you were to put a pot of water onto the stove, crank up the heat, put the lid on, you'd see that the water inside of the pot would bubble, okay? Water molecules would evaporate, they would condense on the lid of the pot, and then that condensation would fall back into the pot again. The two things do not happen separately. In other words, the water doesn't evaporate all the way and then all of the condensate falls back into the pot. The two things are happening at the same time. And that's exactly what this graph is trying to tell you. So this is the point that I would like to stop at for this particular lesson. All right. Please make sure that you update your notes according to the PowerPoint that I'll send through. Please put all of your terminology into your book as well into your glossary page. So for today, just a little bit of an intro, and then also remember to do your rates of reactions question on page 109. Okay. Have a really good day, grade 12s. I'll see you tomorrow in our Zoom.